Hey folks, welcome to the video. This is the second video that is a part 2 to our previous video on simple harmonic motion. Today we're going to see again two different solutions to the simple harmonic motion equation. The first one is a real solution, the second is a complex solution. We're going to relate these two, and then in a subsequent video, a part 3, we're going to relate the solutions from this video to the one from the last one. Let's get to it. Last time we were examining simple harmonic motion. In this equation, d squared x by dt squared equals negative omega squared x. We found that the solutions to this equation go as cosines and sines, at least the real part of the solutions. We also found that there's a complex exponential solution given by c e to the I omega t plus d e to the negative I omega t. We saw that both of these solutions were equivalent, where the real solution was the real part of this complex solution. Today we're going to examine yet another solution to the simple harmonic motion equation. It is again going to be equivalent to the solutions we found last time. In this case, we represent the solution by a singular cosine with a phase, a prime cosine of omega t minus phi, where phi is the phase, and a prime is some amplitude. We're also going to relate this to another complex exponential, a prime e to the I omega t minus phi. Hopefully this explanation and these relations between each of these equivalent solutions gives you a better picture for what simple harmonic motion looks like in the complex plane. Okay, so let's get started. Let's see why this solution over here is a solution to the simple harmonic motion equation. To do that, we would just substitute the solution in to our equation and see if it all works out. If we were to take a first time derivative of this, we get a prime with a negative sign times sine omega t minus phi multiplied by a constant omega. Let's rewrite this like so. And if we were to take a second derivative, we get a second copy of omega, but now a cosine. And we note that this quantity right here is just our original x. So it's negative omega squared x. So in this case, our solution a prime cosine of omega t minus phi satisfies the simple harmonic motion equation. And so it's a solution. Let's also check to see that this solution here, the complex exponential, satisfies it. We take one time derivative to get I omega, a prime e to the I omega t minus phi, and a second time derivative to get I omega squared, a prime e to the I omega t minus phi. I omega squared is just negative omega squared. And again, we notice that this quantity here is just x. So this is negative omega squared x. So both of these are solutions to the simple harmonic motion equation. Recall from last time our discussion on Euler's formula. So let me write that down. Euler's formula relates complex exponentials to cosines and sines. It goes as e to the I theta is cosine theta plus I sine theta. And we can use this to rewrite a prime e to the I omega t minus phi as a prime times the cosine of omega t minus phi plus I times the sine of omega t minus phi. Why? Because we've just set this to be theta, so we get cosine theta plus I sine theta terms. Notice that the real part of this expression right here, the part that is not linked to the imaginary unit, is a prime cosine omega t minus phi. And that's exactly the first solution we started with. So using Euler's formula, we see that the first solution is just the real part of this complex exponential solution. That begs the question, what happened to the imaginary part? And one way to visualize this is to note that e to the I theta is really describing points on the unit circle in the complex plane. Let's try to visualize this. Here's the complex plane. This is the real line. This is the imaginary line. And let's say we have this circle. It's a circle with radius a prime. And we notice that if we were to take this angle to be theta, then this point right here corresponds to a prime cosine theta, and the point on the y, or the imaginary axis here, corresponds to a prime sine theta. If we were to set theta to be omega t minus phi, then a prime e to the I theta, or really a prime e to the I omega t minus phi, would correspond to points on this circle of radius a prime in the complex plane. So what's really going on here? If we had a point on this circle, if we had the following point on this circle, starting out over here, it starts out with some phase phi, so this angle over here would be phi, and it rotates, moves about this circle with some angular velocity omega. So rotations in the complex plane correspond to simple harmonic motion when we take their real part. So that's one good way to visualize simple harmonic motion. It just corresponds to rotations in the complex plane. I hope you guys found that interesting. In the next video, we're going to connect the solutions from this one to the one from the video prior to this. Stay tuned for that. Thanks for watching. Like, subscribe. I'll see you next time.